atoms connect through powerful forces to build everything we know. Welcome. I am Mark from Mentivia. In this module on chemical bonds, we will look at the fundamental forces that hold atoms together to form molecules and compounds. Understanding these bonds is essential for comprehending the structure and function of all matter, especially the complex biological molecules that make up living organisms. Atoms are not content to exist in isolation. They are driven by an inherent desire to achieve stability, often by filling their outermost electron shells, much like the noble gases. This quest for stability is the primary reason why atoms interact and form these crucial connections. Let's begin with ionic bonds. An ionic bond forms when there's a complete transfer of one or more electrons from one atom to another. This typically occurs between a metal atom, which tends to lose electrons, and a nonmetal atom, which readily gains them. When an atom loses electrons, it becomes a positively charged ion, known as a cation. Conversely, an atom that gains electrons becomes a negatively charged ion called an anion. The powerful electrostatic attraction between these oppositely charged ions is what constitutes the ionic bond. A classic example of an ionic bond is the formation of sodium chloride, common table salt. A sodium atom, a metal, has one valence electron it readily gives up to achieve a stable electron configuration. A chlorine atom, a nonmetal, has 7 valence electrons and needs one more to complete its outer shell. Sodium transfers its single valence electron to chlorine. This makes sodium a positively charged ion and chlorine a negatively charged ion. The strong attraction between the positively charged sodium ion and the negatively charged chlorine ion forms the ionic bond, resulting in the stable compound NaCl. Moving on to covalent bonds, these are formed when two atoms share one or more pairs of electrons. This type of bond typically occurs between two nonmetal atoms. By sharing electrons, both atoms can achieve a stable electron configuration, effectively filling their outermost electron shells without the complete transfer of electrons seen in ionic bonds. Covalent bonds are incredibly common in biological molecules, forming the backbone of carbohydrates, lipids, proteins, and nucleic acids. Covalent bonds can vary in how many electron pairs are shared. A single covalent bond shares 1 pair, a double bond shares 2 pairs, and a triple bond shares 3 pairs. Furthermore, covalent bonds can be classified as polar or nonpolar. In a nonpolar covalent bond, electrons are shared equally between atoms, such as in an oxygen molecule O2. However, in a polar covalent bond, electrons are shared unequally due to differences in electronegativity, creating partial positive and negative charges within the molecule. Water, H2O, is a perfect example of a molecule with polar covalent bonds. The oxygen atom is much more electronegative than the hydrogen atoms, meaning it pulls the shared electrons more strongly towards itself. This unequal sharing results in the oxygen atom having a slight negative charge, denoted as delta negative, and the hydrogen atoms having slight positive charges, delta positive. These partial charges are crucial for water's unique properties and its role as the solvent of life. Finally, let's explore hydrogen bonds. Unlike ionic and covalent bonds, which occur within molecules, hydrogen bonds are a type of intermolecular force, meaning they occur between molecules. They are significantly weaker than ionic or covalent bonds individually, but their collective strength and abundance play a crucial role in many biological systems. A hydrogen bond forms when a partially positive hydrogen atom, which is already covalently bonded to a highly electronegative atom like oxygen, nitrogen, or fluorine, is attracted to a partially negative electronegative atom in another molecule. The hydrogen bonds in water are a prime example of their importance. Because water molecules are polar, with partially positive hydrogen atoms and a partially negative oxygen atom, they are strongly attracted to each other. The partially positive hydrogen of one water molecule is attracted to the partially negative oxygen of a neighboring water molecule, forming a hydrogen bond. These continuous attractions are responsible for many of water's unique properties, such as its high boiling point, surface tension, and its ability to dissolve many substances, all of which are essential for life. In summary, we've explored the 3 primary types of chemical bonds: ionic, covalent, and hydrogen bonds. Ionic bonds involve the complete transfer of electrons, forming charged ions that attract each other. Covalent bonds involve the sharing of electrons between atoms, which can be equal or unequal, leading to nonpolar or polar molecules. And hydrogen bonds, while weaker, are crucial intermolecular attractions between polar molecules, especially vital for water and complex biological structures. These bonds are the foundation of chemical interactions and form the intricate chemistry of life. Thanks for watching. If you found this video helpful, be sure to visit mentivia.com, where you'll find a wide range of educational e-learnings, videos, and articles, all completely free. It's your go-to resource for deepening your understanding across science, history, and more. And if you'd like to keep learning with us, don't forget to subscribe to the channel. There's plenty more coming your way.